Welcome, curious minds, to the Deep Dive, your shortcut to being truly well-informed. Have you ever wondered why two molecules made of the exact same atoms can smell completely different? Or, why one is a life-saving drug and its mirror image is just, well, inert? Today, we're unlocking that molecular mystery. We're taking a plunge into the intricate world where a molecule's 3D shape dictates pretty much everything about its personality.
Indeed. It's like we're going on a microscopic safari today, literally diving into this unseen world where molecules perform a dazzling three-dimensional dance. Our guide for this deep dive is a really foundational text in organic chemistry, Advanced Organic Chemistry, Part A, Structure and Mechanisms, 5th edition. We'll be digging into Chapter 2, which covers stereochemistry, conformation, and stereoselectivity. Lots of big words there.
Yeah, that sounds like a mouthful, but trust us, it's absolutely packed with those aha moments. We're talking about everything from why some molecules are right-handed and others left-handed, which is wild to think about, and how just a tiny twist can change a compound's entire personality. Our mission today is to clearly explain these core structures, the fascinating ways they influence chemical reactions, define the technical terms in plain language, and highlight some really powerful applications in, say, drug design and chemical synthesis.
That's right. We'll explore how the fixed arrangement of atoms, what we call configuration, that's like the molecule's permanent ID, and then the flexible shapes molecules can temporarily adopt their conformation, how those fundamentally influence reactivity. And then we'll see how chemists can exploit these principles, these rules, to design reactions that prefer a very specific product. That concept is known as stereoselectivity.
Okay, so to really get this molecular magic, we first need to grasp the basics of how atoms are rigidly fixed in space. Let's begin with the concept of configuration, starting with the immovable world of double bonds.
Configuration, the fixed identity of molecules.
Right. So when carbon atoms link up with a double bond, they're not just 2 points floating around, they're stuck. Stuck in a rigid, flat arrangement. They act almost like molecular billboards, They can't twist freely.
That's a great analogy. The specific way these carbons bond, involving what chemists call sp2 hybridization and that strong bi-bond, well, that locks those two carbons and the four atoms directly attached to them into a perfectly planar setup. It's flat. And this rigidity means that if the groups attached to each carbon are different, you can actually end up with two completely distinct molecules.
And these aren't easily swapped, right? We're talking about a significant energy barrier here. It's not just a quick flip.
Right, like trying to twist a steel beam, as you said. It often takes over 50 kilomole to rotate that bond, which is huge in chemical terms.
Wow.
That's a crucial point. That high energy barrier means these aren't just transient shapes. They are distinct, isolable stereoisomers. Each one has its own unique physical and chemical properties. You can't just twist one into the other without breaking that rigid double bond.
So given that these are distinct molecules, how do chemists actually name them? How do they distinguish between them? I remember the terms cis and trans from, basic chem.
You're on the right track there. Cis and trans work perfectly well when there's only one non-hydrogen substituent on each carbon. Cis means those substituents are on the same side of the double bond, and trans means they're on opposite sides. Simple enough. But you can imagine if you have, say, 3 or 4 different groups around that double bond, cis and trans start to become ambiguous. Which groups are you comparing?
Right. Yeah, I can see how that simple naming system might fall apart when things get more complex. Is there a more universal way, a system that handles all the possibilities?
Absolutely. And this is where the ZE system steps in. It provides a completely unambiguous way to name any double bond, no matter how complex the substituents are. It uses what are called the Kohn-Ingold Prelog, or CIP, priority rules. It sounds complicated, but the idea is simple. You assign priority to the groups attached to each carbon of the double bond based on their atomic number. Higher atomic number means higher priority. If you encounter a tie, say both atoms are carbon, you simply move further out along the chain attached to those carbons until you find the first point of difference. Even multiple bonds, like the double bond in a carbonyl group C double bond O, are handled systematically. You treat them as if they're single bonds to multiple atoms of the same type. So CO counts as C bonded to 2 oxygens for priority purposes.
Fascinating. So it's a step-by-step comparison. Okay, so once you have the priorities on each carbon, what then?
Then it's easy. If the higher priority groups on each carbon are on the same side of that rigid double bond plane, it's a Z isomer. Think of zusammen, which is German for together.
Z for zusammen, together. Got it.
And if the higher priority groups are on opposite sides, it's an E isomer, like Entgegen, German for opposite.
E for Entgegen, opposite. Okay, that makes sense. Z same, E opposite.
Exactly. It's a remarkably intuitive system once you get the hang of assigning those priorities. For instance, in the source, they show an E-isomer where a methyl group, CH3, and a carboxylic acid group, CO2H, are the high priority groups, and they're on opposite sides. And then the Z-isomer has those same high priority groups, CH3 and CO2H, but now they're on the same side.
Okay. And what about compounds that have, say, unshared electron pairs, like in amines or oxomes, where nitrogen forms a double bond? Does that throw a wrench in the works?
Not at all, actually. Those unshared electron pairs are simply assigned the lowest possible priority in the CIP system. Priority 0, essentially. So the ZE rules still apply seamlessly and systematically across a huge range of organic molecules. We see examples like E-azo and Zazo compounds, E-oxim and Z-oxime, E-amine and Z-amine. They all follow the same principles.
That makes it incredibly systematic, which I imagine is absolutely vital for chemists communicating around the world. No ambiguity.
It truly is. The systematic naming is crucial for clarity. In chemistry, slight structural differences can lead to vastly different properties, so you need a precise language. Z and E give us that for double bonds.
So that rigidity of double bonds and their easy or cis-trans labels profoundly shapes a molecule's identity. What happens when atoms form a ring instead? Do we see similar locked arrangements there too?
We absolutely do. In cyclic compounds, just like with double bonds, substituents can be positioned on the same side or opposite sides relative to the general plane of the ring. These are distinct configurations. You can't interconvert them without breaking bonds in the ring. And here, cis, meaning same side, and trans, meaning opposite side, are still used, and they remain unambiguous for naming the configuration relative to, say, a reference group, or just relative to each other. Imagine a molecule like 2-3-dimethyl cyclohexanol. If both methyl groups are pointing up relative to the ring, or both down, it's cis. If one is up and the other down, it's trans. Fixed identities, just like easy.
Okay, now we get to the idea of handedness in molecules. This is where things get pretty mind-bending, I think. This is where that 3D shape really starts to matter in a surprising way.
This concept is absolutely central to stereochemistry, and it's all about non-superimposable mirror images. Think of a tetrahedral carbon atom that's a carbon with 4 single bonds arranged like a pyramid or a jack. If it has 4 different groups attached to it, and they have to be different, you can arrange those groups in 2 ways that are perfect mirror images of each other. But here's the catch. You cannot perfectly stack one on top of the other to make them identical. Try with your hands.
Right. Your left hand and your right hand are mirror images, but you can't superimpose them. So any object or any molecule that can't be perfectly superimposed on its mirror image is chiral. It has this inherent right or left-handed property.
You've got it. And those special atoms, often carbon but sometimes others, with 4 non-identical substituents are called stereogenic centers, or more simply, stereocenters. An older term specifically for carbon is asymmetric carbon. They are the very source of a molecule's handedness, its chirality.
So how do we label this handedness? Is there a naming system like ZE for double bonds? Is this where R and S come in?
Exactly. We use the CIP priority rules again, but for these tetrahedral centers, it's about assigning R, short for rectus, Latin for right or clockwise, or S, short for sinister, Latin for left or counterclockwise. You assign priorities 1 through 4 to the 4 groups attached to the stereocenter, same rules before, based on atomic number. Then you orient the molecule in your mind or on paper, so the lowest priority group, priority 4, is pointing away from you, like it's going into the page. Then you look at the remaining groups, 1, 2, 3. If their priority decreases in a clockwise direction, 1 to 2 to 3, it's the R configuration. If they decrease in a counterclockwise direction, it's the S configuration.
So for you listening, this is literally like giving each chiral molecule a unique R or S name based on its precise 3D structure. It's like a molecular fingerprint for its specific handedness.
That's right. It's a precise way to define their absolute configuration. And this system is crucial because, as we'll see again and again, the handedness of a molecule can completely change its function. Think about trying to use a left-handed glove on your right hand. It just won't fit or work properly. Molecules are often the same way with biological receptors.
And why does this matter so much? You mentioned biological receptors. I've heard it's absolutely critical in pharmaceuticals, for instance.
That's an excellent point. And yes, it's probably one of the most impactful real-world applications. The biological activity of an enantiomeric forms those non-superimposable mirror images of drugs is often drastically different. One enantiomer might be a life-saving drug, while its mirror image could be completely inactive, or worse, actively harmful. Think of R and S carvone, they're enantiomers. One smells like spearmint, the other like caraway or dill. Your nose, which is full of chiral receptors, can easily tell them apart. Our bodies are incredibly sensitive to molecular handedness.
Wow, that's a huge implication. Just a mirror image difference changes the smell entirely. So what's one of the key physical properties that enantiomers differ in, beyond how they interact with, say, our noses?
Well, aside from biological interactions, they primarily differ in how they interact with plane polarized light. This is a physical property called optical activity. One enantiomer will rotate the plane of polarized light in one direction, say clockwise, labeled plus, while its mirror image will rotate it by the exact same amount but in the opposite direction, counterclockwise, labeled manji. We measure this rotation using a device called a polarimeter, and the value we get is the observed rotation, symbolized by alpha.
And then there's something called specific rotation, right?
Yeah.
That sounds like a standardized way to report this rotation,
Yeah.
so everyone gets the same number for the same compound.
Yes, exactly. The specific rotation, symbolized by AW, with usually a subscript for wavelength and superscript for temperature, is the characteristic rotation for a pure enantiomer under standardized conditions. It specifically accounts for the sample's concentration and the path length of the light beam through the sample. This allows for direct comparison between compounds regardless of the specific lab setup or how much sample was used. So if you see a specific rotation value reported in the literature, you know it's a fundamental physical property of that pure enantiomer.
Okay, that makes sense. What if you have a mixture of both enantiomers? Say, an equal 50.50 mix of the RNS forms.
Good question. A perfect 1.1 mixture is called a racemic mixture, or a racemate, because you have equal amounts of the molecule rotating light clockwise and counterclockwise by the same amount. The net effect is zero. A racemic mixture has zero net optical rotation. The rotations cancel out perfectly. What's truly fascinating, though, is that racemic mixtures often have distinct physical properties compared to the pure enantiomers. Things like melting points and solubilities can be different. This is because the R and S molecules might pack differently together in a crystal lattice compared to how pure R or pure S molecules pack. Our source even shows diagrams illustrating this different hydrogen bonding and crystal packing arrangements in a racemic crystal versus an enantiopure crystal for a specific molecule.
That's subtle but profound. So how do you describe the purity of a mixture if it's not 50.50? There's enantiomeric excess, or EE. Sounds like a measure of how much extra you have in one hand.
Yes, exactly. An enantiomeric excess, or EE, is simply the percentage excess of the major enantiomer over the minor one. You calculate it as major enantiomer percent minor enantiomer. So a 75% R, 25% S mixture would have an EE of 50%. Alternatively, if you know the specific rotation of the pure enantiomer, you can calculate the EE from the observed rotation of your mixture, observed. The formula is simply EE observed pure, 100%. The observed rotation directly reflects that excess.
Are there other ways to figure out the EE besides optical rotation? Maybe methods that are more sensitive or work for compounds that don't rotate light much?
Absolutely. Polarimetry is the classic method, but it has limitations. Nowadays, nuclear magnetic resonance, NMR spectroscopy, is incredibly powerful, especially when used with special additives called chiral shift reagents or chiral solvating agents. Various chromatography methods, particularly high-performance liquid chromatography, HPLC, using chiral stationary phases, are also very common and accurate. And capillary electrophoresis is another sophisticated technique. Each method offers unique advantages in terms of sensitivity, speed, the amount of sample needed, and applicability to different types of molecules.
You mentioned specific rotation uses one wavelength. What if you measure rotation as a function of wavelength? That sounds like it would give more information. Is that optical rotatory dispersion, ORD?
You're right, it is. An ORD curve is a plot of the specific rotation versus the wavelength of the light used. The shape of this curve, especially near wavelengths where the molecule absorbs light, is highly characteristic of the molecule's structure and absolute configuration. It's often used in structural studies, particularly by comparing the ORD curve of an unknown compound to those of known molecules to help determine its configuration. Our source shows an example with the UV, ORD, and CD spectra of a specific chiral sulfonium salt.
And circular dichroism, or CD, how does that fit in? Is it related to ORD?
Yes, CD is very closely related. While specific rotation and ORD measures the overall rotation of plane polarized light, circular dichroism, CD, measures how differently a chiral molecule absorbs left versus right circularly polarized light. It's quantitatively expressed as molecular ellipticity. And just like specific rotation, two enantiomers will have exactly opposite CD values at every single wavelength. Their CD spectra look like perfect mirror images of each other across the zero line. Figure 2.3 in the source shows this beautifully with the CD curves for both enantiomers isomers of 2-amino-1-phenol-1-propanone, they are perfectly mirrored.
Okay, so we have these complex 3D structures, especially for molecules with lots of stereocenters like sugars.
Ah.
Are there simpler ways to represent them on a flat piece of paper? Maybe ways that highlight the stereochemistry?
Yes, indeed. Fisher projection formulas are a classic simplification, particularly useful and widely used in carbohydrate chemistry. The convention is to align the main carbon chain of the molecule vertically with the most oxidized carbon atom, like an aldehyde or carboxylic acid, placed at the top. The key rule to remember for interpreting them is that all horizontal bonds in the projection point towards the viewer, out of the page, and all vertical bonds point away from the viewer, into the page. This essentially represents a fully eclipsed conformation of the molecule, even if that's not its most stable real-world shape. It's a specific, defined representation.
That's a crucial detail. So you can't just rotate them freely in space in your mind or flip them over like you might a regular 3D model. There are rules.
Precisely. They can only be reoriented in the plane of the paper by 180 degrees without changing the configuration they represent. If you try a 90-degree rotation or flip it out of the plane, you incorrectly swap what's pointing towards and away, which changes the implied 3D structure. For chirality, Fisher projections often use a D or L designation, which historically references the simplest chiral sugar, glyceraldehyde. If the hydroxyl group, or other key substituent, on the highest numbered chiral center, the one furthest from the top, usually near the bottom, is on the right side of the vertical chain, it's designated D. If it's on the left, it's L.
And for the relative configuration between adjacent stereocenters, like in sugars with multiple chiral centers, there are terms like erythro and threo. These sound like specialized vocabulary.
They are, and they come from the names of 4 carbon sugars, erythros and threos. In a Fisher projection, erythro means that similar substituents on adjacent chiral carbons are on the same side of the vertical chain. Threo means they're on opposite sides. Our source, figure 2.5, illustrates this clearly for 2,000-3,000 trihydroxybutanol, showing both the erythros and threos isomers, and how their Fisher representations relate to their more realistic extended zigzag and Newman projection forms.
It's almost like a chemical shorthand, but you absolutely have to remember the specific rules about what's pointing where and how you can manipulate them to avoid misinterpreting the actual 3D structure.
Indeed. And a critical point to remember, which often trips people up. Because Fisher projections represent an eclipsed conformation, the relative orientation of 2 adjacent substituents is opposite from what you'd see in a more stable, staggered, extended 3D representation, like a zigzag chain. So if 2 groups are anti-180 degrees apart in a staggered conformation, they appear on the same side in a Fisher projection, like erythro. If they are syn or gauche, 60 degrees apart in staggered, they appear on opposite sides in Fisher, like threo. It's vital for accurately interconverting between these representations.
Okay. When we talk about chirality, we often immediately think of that carbon atom with 4 different groups attached, but you hit it earlier. Are there other, perhaps less obvious types of chiral molecules? Where does handedness come from if not just a single tetrahedral atom?
Absolutely. Chirality is a property of the molecule as a whole, and it can arise from various structural features, not just that classic tetrahedral stereocenter. For instance, trigonal nitrogen compounds, like amines, are approximately tetrahedral if you consider the lone pair as a group. They could be chiral, but they undergo rapid pyramidal inversion at normal temperatures. They flip inside out like an umbrella in the wind very, very quickly. This rapid interconversion means you usually can't separate their enantiomers. They're fleetingly chiral, but racemize too fast to isolate.
Okay, so amines usually aren't chiral in practice. But what about allenes? They have that weird CCC bonding arrangement that looks linear. Can they be chiral?
Allenes are fascinating. They have 2 adjacent carbon double bonds, CCC. They can be chiral if they have non-identical substituents at both ends, meaning the groups on the first sp2 carbon are different from each other. And the groups on the third sp2 carbon are different from each other. This is because the pi bonds of the 2 double bonds are perpendicular to each other. This forces the substituents on the terminal carbons to lie in planes that are also perpendicular. The result is a non-planar structure whose mirror image is non-superimposable. Imagine 2 propellers attached back to back, but twisted 90 degrees relative to each other.
That's a cool structure. And then there are molecules with a definite screw-like shape, like helices. That sounds like something out of molecular art.
Yes, these are truly captivating examples of chirality arising from the overall molecular shape. Steric factors shear crowding can force a molecule to adopt a screw-like helical shape. This leads to distinct right-handed, P for plus, or left-handed M for minus forms. A prime example is found in 11,1 binaphyl compounds like banal, which is a diol, and binap, a diphosphine. They exhibit something called a tropisomerism. This means rotation around the single bond connecting the two naphthyl rings is severely restricted due to steric hindrance between hydrogen atoms on the rings. This prevents them from flattening out and locks them into stable, non-planar, and antimatter conformations.
I've definitely heard of binal and binap being super important in catalysis, especially asymmetric catalysis.
They are incredibly important. They serve as immensely useful chiral ligands in organometallic catalysts, particularly for enantioselective hydrogenations, which we'll delve into later. Their inherent stable-handedness is transferred directly to the reaction environment, enabling chemists to create specific enantiomers of products with very high selectivity. A truly spectacular example of this kind of helical chirality is hexahelicene. Here, 6 benzene rings are fused together in an angular way. The molecule literally cannot lie flat due to the ends bumping into each other, forcing it into a helical non-planar shape. Its specific rotation is incredibly high, around 3,700 degrees, demonstrating its extreme handedness. While it can be racemized by heating, it requires a significant activation energy, around 36 kilocalmol, for the terminal rings to slip past each other.
Amazing. What about spiro compounds? Those are rings that share just a single atom, right? Can they be chiral?
Many spiro compounds are indeed chiral, provided that neither ring contains a plane of symmetry passing through the shared spiro atom. Their unique, often twisted, non-planar geometry means they cannot be superimposed on their mirror images. S plus, spiro 3000, 3-hepta-1-Valier-5-diaron, is a well-known example cited in the text.
And even some simple-looking cyclooctanes can be chiral. You mentioned E-cyclooctane earlier. That seems like a stretch for just an 8-membered ring with a double bond.
It's not a stretch at all.
Sure.
J-cyclooctane is chiral, and it's a classic example. Its trans double bond, when forced into the constraints of an 8-membered ring, twists the ring into a non-planar, non-superimposable structure. Its mirror image is distinct. It also undergoes thermal racemization, a process where the double bond effectively slips through the ring to form the enantiomer. The larger and more flexible the ring containing a trans double bond, the easier this process becomes. The half-lives for racemization vary dramatically, from hours for E-cyclooctane to essentially immediate racemization for larger rings like E-cyclotene.
Okay, so we've covered quite a few ways molecules can be chiral or handed. What makes a molecule not chiral? What's the opposite of handedness? Is it just about symmetry?
Indeed. Molecules that are achiral, meaning they are not chiral, possess certain elements of symmetry that guarantee their mirror images are perfectly superimposable. The most common and usually easiest to spot element of symmetry is a plane of symmetry. This is an imaginary plane that divides the molecule into 2 identical halves, where each half is the mirror image of the other. For example, 2-propanol, isopropyl alcohol, has a plane of symmetry that cuts through the central carbon, the OH group, and the CH bond, making the 2 methyl groups reflections of each other. Therefore, 2-propanol is achiral.
Okay, a plane of symmetry makes sense. What about a center of symmetry? That's a bit trickier to visualize, I think.
It is less common, but equally important for determining achirality. A center of symmetry, or inversion center, is a point within the molecule such that if you draw a line from any atom through that center and extend it an equal distance beyond, you encounter an identical atom. An example given in the text is trans, calores 2,4-aldehydoxychloro-1-FR3-dimethylcyclobutane. This specific isomer is achiral because it possesses the center of symmetry right in the middle of the ring, even though it lacks any plane of symmetry. It's still superimposable on its mirror image because of that central inversion point.
And this whole idea of symmetry relates directly to meso compounds, right? Like mesotartaric acid, which always comes up. It sounds like an exception to the rule because it has chiral centers but isn't chiral overall.
Meso compounds are a fascinating and important case. They contain stereogenic centers, usually 2 or more, but the molecule as a whole is achiral because it possesses an internal plane or center of symmetry that relates those stereocenters. Mesotartaric acid is the classic example. It has 2 stereocenters, but it's optically inactive. Why? Because it possesses a plane of symmetry in its eclipsed conformation, easily seen in a Fisher projection, and a center of symmetry in its anti-staggered conformation. These internal symmetry elements effectively cancel out the chirality, making the molecule superimposable on its mirror image.
So the take-home message is, if a molecule, including cyclic ones, has either a plane of symmetry or a center of symmetry, it's considered achiral, even if it contains stereogenic centers.
Correct. Even when we sometimes represent cyclic molecules as flat planar structures just to visualize the cis-trans relationships between substituents, the presence of these internal symmetry elements in the actual 3D molecule is what ultimately determines achirality. It's the overall molecular symmetry that counts.
Conformation? The flexible shapes of molecules?
Okay, so we've established that some molecules have a fixed-handedness or configuration, a fundamental identity that doesn't change without breaking bonds. That's their configuration. But what about the molecules that do change their shape? The ones that twist and turn and wiggle around in a constant dance? That's where we enter the dynamic world of conformation.
Precisely. This is all about the different spatial arrangements of atoms in a molecule that can be interconverted simply by rotation around single bonds. These are generally low energy changes that don't involve breaking any bonds. Let's start with the simplest example, ethane, CH3CH3. Its two methyl groups can rotate relative to each other around that central carbon single bond.
Right, I remember staggered and eclipsed forms from way back. Are those the key players here, the main shapes it adopts?
They absolutely are. The staggered conformation is the lowest energy state, the most stable one. Here, the hydrogens on the adjacent carbons are as far apart as possible when you look down the CC bond. The eclipse conformation is the highest energy state, the least stable. Here, the hydrogens are directly aligned with each other, leading to increased repulsion or what we call torsional strain. There's an energy difference, a rotational barrier, between these two extremes. For ethane, it's about 2.88 kilogall. This isn't huge, so rotation happens rapidly at room temperature, but it means molecules spend almost all their time in or very close to the stable staggered conformations.
And you mentioned the stabilization of the staggered form is often attributed to something called hyperconjugation. Can we unpack that just a bit more?
Sure. Hyperconjugation, in this context, is a stabilizing electronic interaction. Think of it as a subtle sharing of electron density. Electrons in a filled carbon-hydrogen sigma bonding orbital on one metal group can slightly delocalize or overlap with an adjacent empty carbon-hydrogen antibonding sigma on the other metal group when they are in that staggered antiparaplanar arrangement. This tiny bit of electron delocalization lowers the overall energy and helps stabilize the staggered conformation relative to the eclipsed one, where this optimal orbital overlap isn't possible. It's a reminder that even single bonds have a subtle electronic life beyond just holding atoms together.
Okay, that adds another layer. So what happens when we add more carbons? Like in N-butane, CH3, CH2, CH2, CH3, does it just get more complicated with more possible shape?
It does get a bit more complex, yes. N-butane's rotational profile around its central C2-C3 bond is more involved, but still follows the same basic principles. It has 3 energy minima, all corresponding to staggered conformations. The anti-conformation, where the two bulky methyl groups are 180 degrees apart, is the most stable, lowest energy, because it minimizes van der Waals repulsions between those methyls. The two gauche conformations, where the methyl groups are only 60 degrees apart, are slightly higher in energy by about 0.6 kilocall due to that minor steric clash between them. And its 3 energy maxima correspond to eclipse conformations, with the highest energy barrier occurring when the two bulky methyl groups are directly eclipsed with each other. That's the most unfavorable arrangement.
So van der Waals repulsions, essentially, atoms bumping into each other if they get too close, play a really big role in determining a molecule's preferred shape, its conformation.
A very significant role, especially as groups get larger. And we see this trend continue with more complex alkanes. Substituting a hydrogen with a methyl group generally increases the rotational barrier by maybe 0.4 to 0.6 kilocall. For instance, propane's barrier is a bit higher than ethane's, around 3.4 kilocall. And something like hexamethylethane, which has 3 methyl groups crowding around each end of the central bond, has a massive barrier about 8.4 kilocall. It's much harder to twist past those bulky groups.
How do scientists even measure these tiny energy differences and these incredibly rapid rotations? They must happen in fractions of a second.
We use a whole arsenal of sophisticated experimental techniques. These often involve various types of spectroscopy. Microwave spectroscopy is very sensitive to the precise rotational constants of a molecule, which depend on its geometry. Electron diffraction in the gas phase can give us bond lengths and angles. Ultrasonic absorption can measure energy differences between conformers. And infrared IR spectroscopy is often used, especially at low temperatures, where you can sometimes freeze out and observe individual conformers, allowing measurement of their relative stabilities.
Okay. What about alkenes? Like propene, CH3, CH2, does rotation around the single bond next to the double bond have preferences, even with that rigid double bond there?
Yes. Even with the double bond fixing part of the molecule, there are still rotational preferences for for the groups attached via single bonds. Propene, which just has a methyl group attached to the double bond, has two main conformations regarding the methyl group's rotation relative to the double bond, one called eclipsed and one called bisected. The eclipsed conformation, where one CH bond of the methyl group eclipses the double bond, is actually preferred by about 2 kilocalmol. This represents the barrier to methyl group rotation. You can sort of conceptualize this using an analogy. If you think of the pi bond as two banana bonds, the eclipsed propene conformation corresponds to a staggered ethane-like alignment between a CH bond and a banana bond, which is favorable. The bisected corresponds to an unfavorable eclipsed alignment.
And with more substituents, say in 1-butene, where you have an ethyl group attached,
more conformations arise, naturally, but the eclipsed type generally remains more stable than the bisected type for similar reasons. Studies show subtle energy differences even between different eclipsed forms. For 1-butene, one eclipsed form, conformation B in the text, is slightly more stable than another, conformation A, due to minimizing van der Waals interactions between the vinyl group and the terminal methyl group. And as you increase the size of the group attached further down the chain, like in 4-cider-dimethyl-1-pentene, which is a bulky T-butyl group, the preference for specific eclipse conformations that minimize steric strain becomes even more pronounced. The molecule twists to keep the bulkiest parts away from the double bond.
What about carbonyl compounds, aldehydes and ketones with the CO group? Do they follow similar rules for rotation around adjacent single bonds?
Yes, the principles of rotational barriers and preferred conformations definitely apply there too. In propanol, CH3CH2CHO, for example, the methyl group actually prefers to be eclipsed with the carbonyl group, CH2CO, in the most stable conformation. There's an energy difference of about 0.9 kilocaramel compared to the conformation where a hydrogen is eclipsed with the carbonyl. However, with very bulky alkyl substituents attached to the alpha carbon, this preference can reverse. The hydrogen-eclipsed conformation might become favored to relieve steric strain between the bulky group and the carbonyl oxygen. For ketones like 2-butanone, the rotational energy profile around the C2-C3 bond shows preferred staggered conformations, influenced by both steric factors and the electronic nature of the carbonyl group.
And how about conjugated systems like 1,4,3-butadiene, where you have alternating double and single bonds? That sounds like it adds another layer.
It absolutely introduces a new layer. The conjugation itself, the overlap of the pi systems across a single bond, provides extra stability. 1,50-rajapidine largely exists in an S-trans conformation. Here, the two double bonds are coplanar in the same plane and point in opposite directions relative to the central single bond. S-keys refers to the single bond. There's a significant energy barrier, about 3.9 kilogenerol, to rotate around that central single bond to convert the non-planar skew conformation into the stable S-trans form. This barrier highlights the energetic benefit, the stabilization, gained from maximizing that pi electron delocalization in the planar sans shape.
So that transform is generally more stable than the cis form, where both double bonds point the same way.
Generally, yes. For brutadiene itself, S-trans is typically about 2-5 kmol lower in energy than Cs. However, for related systems like unsaturated ketones, CCCSCO, the equilibrium between C-strands and Cs can depend heavily on van der Waals interactions between substituents. Adding larger alkyl groups can progressively increase the preference for the Cs form if the S-trans form becomes destabilized by a significant steric clash. A classic example is 4-methylpent-3N2,1, also known as mesodyl oxide. Here, an unfavorable steric interaction between two methyl groups in the Cs-trans form causes the equilibrium to significantly favor the C-Cs conformation, where that clash is avoided.
Okay, so that covers rotation in chain-like molecules. But rings add a whole other level of complexity, right? They're not just freely rotating, they're constrained into a loop.
Exactly. Rings introduce constraints that lead to other types of strain, primarily angle strain and torsional strain. Angle strain arises when the bond angles within the ring are forced to deviate from their ideal values, like 109.5 degrees for sp3 hybridized carbon. Torsional strain comes from eclipsing interactions between atoms on adjacent carbons around the ring, similar to what we saw in ethane. Cyclohexane is the classic and really important example here.
Right, the famous chair conformation of cyclohexane. That's the most stable one, isn't it? It seems to be the star of the show when talking about rings.
It absolutely is the star. The chair conformation of cyclohexane is remarkable because it achieves near-perfect tetrahedral bond angles, close to 109.5 degrees, and it completely minimizes torsional strain because all the CH bonds along the periphery are perfectly staggered relative to their neighbors. It's essentially strain-free, like a perfectly balanced structure. However, and this is key, cyclohexane isn't static. It can rapidly invert or flip between two equivalent chair forms. You can visualize it like flipping an umbrella inside out and back again. This process is called conformational inversion or ring inversion. The energy barrier for this flip is relatively low, about 10.8 kilocoulomb, so it happens incredibly rapidly at room temperature, thousands, even hundreds of thousands of times per second.
So it's not locked into one chair conformation, but constantly dancing between two equivalent chairs.
That's exactly right. It's a dynamic equilibrium. The molecule passes through higher energy shapes during this flip. The highest point, the transition state, is thought to be a half twist or half chair form. Other less stable shapes, like the boat conformation and the twist or twist boat conformation, are also intermediates along this inversion pathway. They are significantly higher in energy than the chair due to considerable torsional strain, and also van der Waals repulsions, particularly the flagpole interaction, where two hydrogens point towards each other across the ring in the pure boat form. The twist boat is slightly more stable than the boat.
What happens when you put a substituent, say a methyl group, onto that cyclohexane ring? Does it still prefer the chair form? And where does the substituent go?
This is where the crucial concepts of axial and equatorial positions come in. In a chair conformation, there are two types of positions for substituents. 6 point straight up or down, roughly parallel to an imaginary axis through the ring. These are axial. The other 6 point out towards the periphery, roughly in the equator of the ring. These are equatorial. When you add a substituent, it overwhelmingly prefers to occupy an equatorial position. Why? Because the axial position suffers from unfavorable steric interactions, called 1-3 diaxial interactions. An axial substituent bumps into the two axial hydrogens located 3 carbons away on the same side of the ring. For a methyl group, this destabilization is about 1.8 kilocoulomb. Placing it in the equatorial position avoids these clashes, making that conformer much more stable.
How do chemists actually measure these energy differences between axial and equatorial forms and figure out the incredibly rapid rates of ring inversion? It sounds like you'd need some seriously advanced technology.
NMR spectroscopy, particularly variable temperature NMR, is incredibly valuable for this. At high temperature, say room temperature, the ring inversion is so fast on the NMR timescale that you see only average signals for the axial and equatorial protons. They're swapping places too quickly to be distinguished. But if you cool the sample down significantly, often to below -60 degrees C or even lower, the ring flip slows down dramatically. Eventually, it becomes slow enough that the NMR can see both the axial and equatorial protons as distinct species with different chemical shifts. By measuring the relative areas of these separate signals at low temperature, we can directly determine the equilibrium constant between the two conformers, and thus calculate the conformational free energy difference, often called the A value or Nijten-Jeet. Furthermore, by analyzing how the NMR spectrum changes as you warm the sample up, a technique called line shape analysis, we can even determine the activation energy barrier for the ring inversion process itself.
So the book mentions chlorocyclohexane, and you can actually freeze out the equatorial conformer at -150 degrees C and see just that one by NMR. That's truly incredible precision. It's like stopping molecular motion.
That's a really striking example from the source material. Yes, at such extremely low temperatures, chlorocyclohexane can be crystallized to yield almost exclusively the more stable equatorial isomer. And its NMR spectrum vividly confirms this by showing only the characteristic signals of that single conformer. Then, as you slowly warm it up, the equilibrium rapidly reestablishes, and the signals for the axial conformer reappear. It perfectly illustrates how profoundly temperature affects these dynamic molecular processes. The text even includes a table showing the calculated half-life for the conformational inversion of chlorocyclohexane at various temperatures. It ranges from about 1.3 by 10 to 5 seconds, 13 microseconds, at 25 degrees C, to several hours at -120 degrees C, and an astonishing 22 years at -160 degrees C. It's like molecular time travel, where temperature controls the speed of this internal dance.
Wow. So what does a large negative GC value or A value tell us about a substituent?
It tells us there's a very strong preference for that substituent to be in the equatorial position. The larger the A value, which is the energy cost of being axial, the more overwhelmingly the equilibrium favors the equatorial conformer. For instance, a tert-butyl group, a very bulky group, has a very large A value, greater than 4.7 kiloball. This makes it a powerful, conformationally biasing group. Its sheer bulk effectively forces, or at least heavily biases, the entire ring into the conformation where the T-butyl group can sit comfortably in the spacious equatorial position.
But bias isn't the same as locked, right? It can still technically flip, just very rarely finds itself in the axial form.
That's a very important distinction. It's not truly locked because ring inversion can still occur. The pathway exists. It just means the conformer with the bulky group axial is so high in energy, so unstable, that it's populated only to a minuscule extent at equilibrium. The barrier to inversion might still be similar, but the energy difference between the two chair forms is huge. For molecules with two or more substituents, like in dimethylcyclohexenes, the conformational preferences A values of the individual groups essentially add up. The most stable conformer will be the one that places as many bulky groups as possible in equatorial positions, minimizing the total strain from unfavorable 1:3 diaxial interactions.
Okay, what about fused ring systems, like decalins? They sound like two cyclohexanes stuck together. How does that affect the flipping?
Decalins are indeed two fused cyclohexane rings, and they're excellent for illustrating how fusion affects conformational mobility. There are two isomers, transdecalin and cisdecalin. Transdecalin, where the rings are fused via two equatorial bonds, is conformationally rigid or locked. Its rigid fusion prevents the necessary bond rotations for a chair-chair inversion to occur in either ring. This makes transdecalin an ideal model system for studying the intrinsic properties of groups held in truly fixed axial or equatorial environments. Cisdecalin, however, where the rings are fused via one axial and one equatorial bond, is conformationally mobile. It undergoes ring inversion, flipping between two equivalent chair forms at a rate only slightly slower than cyclohexane itself, with a slightly higher energy barrier, around 12-13 kilocoulombs.
So for you listening, really understanding these precise conformational preferences, axial versus equatorial, chair flips, ring strain, is absolutely key to predicting how these molecules will behave, how they'll react, and even how they might fit into a biological receptor site.
Absolutely. Even subtle energetic differences, often just a kilocalorie or two, can dictate which conformation is present and therefore how a reaction proceeds. Molecules tend to react via their most stable or most accessible conformations. And knowing those preferred shapes gives chemists powerful predictive and design tools.
Okay, beyond the well-behaved cyclohexane, what about other ring sizes? I imagine smaller rings like cyclobutane or larger rings like cyclooctane have their own unique challenges and shapes due to strain.
They certainly do. The total strain energy for any given cyclooctane is a combination of different factors. Primarily angle strain, when bond angles deviate from the ideal tetrahedral 109.5 degrees, torsional strain, from eclipsing interactions between adjacent bonds, and sometimes transangular van der Waals repulsions, atoms bumping into each other across the ring. Our source provides a useful table comparing the strain energies for various cycloalkanes. It clearly shows that cyclopropane, with 60-degree angles, and cyclobutene are highly strained, around 28 and 26 kilomole respectively. Cyclopentane has moderate strain, while cyclohexane has very little, less than 2 kilomole, making it the ideal ring size in terms of minimizing classical strain. Medium rings, C7, C11, often have significant strain again due to a combination of angle, torsional, and transangular strain, before larger rings, C12+, become flexible enough to adopt relatively strain-free conformations.
Cyclopropane, for instance, is famously planar because it only has 3 carbons, so there's no real conformation question there, but it's incredibly strained due to those 60-degree angles. It's like a molecular triangle constantly wanted to spring open.
It is planar, yes, and its high strain arises primarily from that severe angle strain. Forcing C3 carbons into 60-degree angles is very unfavorable. This strain is often explained using the concept of bent bonds or banana bonds, where the electron density in the CC bonds is displaced outwards from the internuclear axis. This unusual bonding leads to its high reactivity. Cyclopropane readily undergoes ring opening reactions. It also has shortened CC bonds and slightly opened HCH angles compared to typical alkanes. And cyclobutane, it has 4 carbons. Is it planar, or does it try to relieve some of that strain by puckering up a bit? No, cyclobutane is definitely not planar. A planar cyclobutane would have 90-degree angles, still strained, but also severe torsional strain from all HCH bonds being eclipsed. To relieve this torsional strain, cyclobutane adopts a puckered or folded conformation. In this puckered form, substituents can occupy positions that are somewhat analogous to axial and equatorial, though the energy differences and barriers to inversion, flipping between puckered forms, are much smaller than in cyclohexane. It's more flexible, but still strained.
What about cyclopentane, 5 carbons? It seems like it could be planar with angles close to the ideal 108 degrees for a regular pentagon, but I recall it's actually not planar either.
You're right, it's non-planar. While a planar cyclopentane would have minimal angle strain, it would suffer from considerable torsional strain because all 10 CH bonds would be eclipsed. So to relieve this torsional strain, cyclopentane adopts flexible, non-planar conformations. The two most commonly described are the envelope form, where one carbon is out of the plane of the other four, and the half-chair form, where two adjacent carbons are out of the plane. These forms rapidly interconvert through a low-energy process called pseudorotation, where the puckering effectively moves around the ring like a wave.
And as the rings get even larger, say beyond cyclohexane, does the complexity just explode with possible shapes?
It does. For rings larger than cyclohexane, medium and large rings, the number of possible low-energy conformations increases significantly. They become much more flexible. For example, cycloheptane's most stable conformation is calculated to be the twist chair. Cycloheptane has a very complex conformational landscape with at least 5 stable energy minima identified experimentally and computationally, with the boat chair conformation generally being the most stable. The interconversion barriers between these various conformers in larger rings are typically quite low, often in the range of 5-8 kilocalmol, meaning they are very dynamic and flexible at room temperature.
Wow, it sounds like it would be incredibly difficult to keep track of all these specific shapes for larger rings.
It can be, but there's an interesting and simplifying concept that emerges, especially for larger rings, like C10 and above. They tend to adopt conformations that mimic sections of the highly stable diamond lattice. Diamond is the most stable structural arrangement for a large infinite array of sp3 hybridized carbon atoms. Adamantane, a familiar rigid polycyclic hydrocarbon, is a perfect molecular example. It's essentially a small cage-like piece of the diamond lattice.
So these large, flexible rings actually try to fold themselves up in ways that incorporate those stable, strain-free chair cyclohexane-like conformations, almost like building blocks within the larger ring.
Precisely. This idea has been explored through systematic topological analysis and confirmed by detailed molecular mechanics computations for cycloalkanes, ranging from C10 all the way up to C24. Cyclododecane, C12, is often cited as an example where its most stable, calculated conformation clearly resembles a compact, symmetrical structure derived from the diamond lattice, effectively incorporating multiple chair-like fragments.
Okay, this leads to a practical question. How do chemists actually figure out all these stable conformations and their relative energy differences, especially for really complex molecules? Do they just build plastic models and guess, or is there a more systematic way?
Well, physical models are still useful for visualization. But thankfully, we've moved far beyond just guessing. This is where molecular mechanics comes in as a powerful computational tool. It provides a systematic and quantitative approach to analyzing molecular conformation and predicting molecular shapes and energies. It essentially treats a molecule as a collection of atoms held together by forces, much like a macroscopic system of balls connected by springs.
Okay, let's unpack this. What is molecular mechanics at its core? How does it actually work computationally?
The fundamental idea driving it is that a molecule will naturally adopt the geometry, the conformation, that minimizes its total strain energy, also called steric energy. This total energy is calculated as a sum of several distinct energy contributions, each modeled by a mathematical function. 1. Energy from bonds being stretched or compressed from their ideal equilibrium lengths. 2. Energy from bond angles being bent or distorted from their ideal angles, like 109.5 degrees for sp3 carbon. 3. Torsional strain energy arising from rotations around single bonds, representing the barriers between staggered and eclipse forms. 4.
And crucially, non-bonded interactions between atoms that aren't directly bonded.
And those non-bonded interactions include things like atoms physically bumping into each other if they get too close, van Waals repulsion, but also those weaker attractive forces, right? Yes, exactly. The non-bonded term accounts for both van der Waals repulsions at very close distances and the attractive London dispersion forces that operate at slightly longer distances due to temporary fluctuations in electron clouds. Electrostatic interactions between polar bonds, bond dipoles, are also included and can be very important. The model uses potential energy functions derived from classical mechanics. For example, the energy penalty for stretching a bond or bending an angle typically increases as the square of the distortion from its ideal value, behaving much like a spring obeying Hooke's law. Torsional strain is usually modeled as a sinusoidal function, like a cosine wave, of the torsion angle, reflecting the periodic nature of rotational barriers we discussed for ethane and butane.
How accurate are these calculations? Can they really pinpoint these subtle energy differences and predict structures reliably?
They have become remarkably accurate, especially for well-parameterized systems like hydrocarbons. Modern molecular mechanics, force fields, like the MM4 system developed over many years by Norman Allinger and his co-workers, can calculate geometries of saturated hydrocarbons often to within 0.005 A that's 5/1000ths of an angstrom, for bond lengths, and less than 1 degree for bond angles compared to experimental values. They can even calculate thermodynamic properties like heats of formation to very high accuracy, often within a fraction of a kilocalorie per mole for many organic molecules.
So it's not just useful for predicting the shapes of stable, everyday molecules. Can it model those fleeting, unstable intermediates we talked about earlier, like carbocations?
Yes, absolutely. Molecular mechanics methods have been parameterized and successfully applied to calculating the structures and stabilities of unstable reactive intermediates like carbocations and radicals. And importantly, it's often combined with more computationally intensive quantum mechanical methods like molecular orbital theory or density functional theory, DFT, for studying transition structures, those high-energy fleeting states that molecules pass through during the course of a chemical reaction. In these hybrid QMMM approaches, the reacting core of the molecule, where bonds are breaking and forming, is treated with the more accurate quantum mechanics, while the larger, less reactive parts of the molecule, like solvent or protein scaffold, are handled efficiently by molecular mechanics. This approach is crucial for understanding complex processes like enzyme catalysis.
That sounds like an incredibly powerful toolkit for chemists, allowing them to not just analyze, but also predict and design molecules and reactions with amazing precision.
Stereochemistry and action reactions and selectivity.
Okay, so all this fascinating discussion about a molecule's fixed shape, configuration, and its flexible shapes, conformation, leads us directly to the heart of chemistry. How do these structural features influence how molecules actually react? This brings us to terms like stereoselective and stereospecific reactions. They sound similar, but I imagine there's an important distinction we need to understand.
There is a crucial difference, yes, and it directly impacts how chemists design and predict the outcomes of synthetic reactions. If a reaction shows a preference for forming one stereoisomeric product over other possible stereoisomers, it's called stereoselective. It doesn't have to be 100% preference, just a measurable bias. For instance, we mentioned catalytic hydrogenations often favor adding hydrogen from the less hindered face of a double bond. If this leads to, say, 80% of one stereoisomer and 20% of another, the reaction is stereoselective. It selects one outcome more than the other.
Okay, so stereoselective is about preference. What about stereospecific? That sounds much more definitive, maybe like there's only one possible stereochemical outcome dictated by the starting material?
You've got it exactly right. A reaction is stereospecific when stereoisomeric reactants each provide distinct, different stereoisomeric products. And the reaction mechanism dictates a direct, predictable geometric relationship between the reactant's configuration and the product's configuration. The classic textbook example is the SN2 substitution reaction. It always proceeds with an inversion of configuration at the reacting carbon center, like turning an umbrella inside out stereochemically. So if you start with a reactant that has the R configuration at that center, the SN2 mechanism guarantees you will get a product with the S configuration, assuming the priority rules for the substituents don't coincidentally change. There's no mixture, no loss of information. The stereochemistry of the starting material specifically determines the stereochemistry of the product via the mechanism.
So following that logic, if the reaction mechanism were to shift, say from a concerted SN2 to a stepwise SN1 mechanism involving a carbocation, you would lose that tight stereospecificity.
Precisely. SN1 reactions typically lead to stereorandomization or racemization. Why? Because they proceed through a flat, planar carbocation intermediate. Once that intermediate is formed, the incoming nucleophile can attack it from either face, top, or bottom with roughly equal probability. This leads to a mixture of stereoisomeric products, often close to a 50.50 racemic mixture, completely scrambling the stereochemical information from the starting material. Another familiar example involves addition reactions to double bonds. If a specific mechanism dictates syn addition, both new groups add to the same face, or anti-addition, groups add to opposite faces, then starting with an E alkene versus a Z alkene will lead to different, distinct stereoisomeric products. For example, anti-addition to a Z alkene might give a racemic pair, while anti-addition to the corresponding E alkene gives a mesocompound. This direct, predictable link between reactant geometry, E or Z, and product geometry, syn-antidiastereomers or meso, via the mechanism is the hallmark of stereospecificity.
Okay, let's look at some specific examples. Hydrogenation is a really common reaction, adding hydrogen across a double bond using a catalyst. How does the concept of stereochemistry play a role there? Is it selective or specific?
Catalytic hydrogenation is generally stereoselective and often highly so. Whether you're using heterogeneous catalysis, like palladium metal on a solid carbon support, or homogeneous catalysis using soluble transition metal complexes like Wilkinson's catalyst or cationic rhodium or iridium complexes. The hydrogen usually adds preferentially from the less hindered face of the double bond. And critically, it almost always adds in a syn fashion, meaning both hydrogen atoms add to the same side of the double bond plane.
So you can imagine the molecule kind of landing or absorbing onto the catalyst surface via its less crowded side, and then the hydrogen atoms from the surface are delivered to that exposed face.
That's the general picture, especially for heterogeneous catalysis, yes. The alkane first coordinates to the metal surface, forming a pi complex. Then, hydrogen atoms, which are also absorbed onto the metal, are transferred sequentially, but usually quickly, to the same face of the coordinated alkane. A really powerful aspect of this, especially in homogeneous catalysis, is that certain functional groups already present in the molecule, like hydroxyl or ether groups, can act as syn-directing groups. They can coordinate to the metal catalyst center, essentially anchoring the molecule in a specific orientation and thereby favoring hydrogen addition from the same side as that directing group, even if that side isn't intrinsically the least hindered overall face of the double bond.
That sounds like a very practical handle for chemists to control the outcome. It's like having a built-in molecular steering wheel guiding the hydrogen addition.
It is indeed a powerful tool for controlling stereochemistry. For example, the text mentions that with the iridium-based homogeneous catalyst known as Crabtree's catalyst, cyclic alkenes containing a nearby hydroxyl group, cyclohexanols, show excellent stereoselectivity for hydrogen delivery syn to that hydroxy group. You can get product ratios as high as 99.1 favoring the isomer formed by addition from the same side as the OH. This is a fantastic way to control the 3D outcome by carefully choosing the substrate or the catalyst system.
Okay, let's switch gears to reducing ketones, CO, to alcohols, CHOH. How does the shape of a ring, like cyclohexane, affect which stereoisomer of the alcohol you get? I imagine it's not always straightforward which face the reducing agent attacks.
It's actually quite fascinating and sometimes counterintuitive. For relatively unhindered cyclohexanones, when you use small hydride reducing agents like sodium borohydride, NaBH4, or lithium aluminum hydride, LiLH4, the hydride nucleophile actually prefers to approach the carbonyl carbon from the axial direction, even though that path might appear more sterically congested by the axial hydrogens on the ring. This preferred axial attack leads primarily to the formation of the equatorial alcohol product.
Wait, that seems backward. Why attack from the more crowded axial face rather than the seemingly more open equatorial face? What's overcoming the steric hindrance?
It's believed to be primarily due to torsional effects in the transition state, an idea championed by Felkin and Ann. In the starting ketone, the CO double bond is almost eclipsed with the CH bonds on the adjacent carbons, C2 and C6 of the ring. As the hydride approaches axially, the oxygen atom can bend away from the ring, relieving this torsional strain as the carbon rehybridizes towards sp3. In contrast, if the hydride were to approach equatorially, the oxygen atom would have to move through a more fully eclipsed arrangement with those adjacent CH bonds during the reaction, actually increasing torsional strain in the transition state. So for small nucleophiles, avoiding this increase in torsional strain is thought to be more important than avoiding the minor steric clash of axial approach.
So it's not just about atoms physically bumping into each other. There are these more subtle electronic or orbital strain effects at play.
Not always just about bumping, no. However, the situation can completely reverse if you switch to bulkier hydride-reducing agents, like lithium trisec-butyl borohydride, L-selectride, or other highly substituted alkyl borohydrides. Or if the ketone itself has bulky axial substituents that create additional crowding near the axial face. In these cases, steric hindrance becomes the dominant factor. These bulky regions are significantly hindered by the 1,3 diaxial hydrogens, or substituents, if they try to approach axially. Therefore, they strongly prefer the less hindered equatorial approach, leading predominantly to the formation of the axial alcohol product. This is a clear case of steric approach control.
So it's a delicate balance. It's between those torsional effects that favor axial attack for small regions and steric hindrance, which forces bulkier reagents towards equatorial attack.
Exactly, it's a competition. And our sources table 2.4 illustrates this beautifully. It shows data for reducing various cyclohexanones with different hydrides. As you increase the steric bulk of the hydride region, from NaBH4 to LaLH4 to L-selectride, or add bulky substituents to the ketone ring, you see a systematic shift in the product ratio from predominantly equatorial alcohol via axial attack towards predominantly axial alcohol via equatorial attack. And it's not just cyclohexanones. Rigid bicyclic systems like norbornenones also show predictable stereoselectivity. In the parent norbornone, attack occurs preferentially from the exophase, the less hindered outside face of the bicyclic system. However, adding bulky 7,7-dimethyl substituents can block the exophase and reverse this preference, making attack from the endoside more favorable. It all depends on the specific steric environment around the carbonyl.
Okay, now what if you have a stereogenic center right next to the carbonyl group in an acyclic non-ring ketone or aldehyde? How does that existing chirality influence where a nucleophile adds to the CO? It seems like that nearby handedness would have to have some impact.
It absolutely does, and this is a fundamental concept in asymmetric synthesis. When a nucleophile adds to a carbonyl group adjacent to a stereocenter, it leads to the formation of a new stereocenter, resulting in two possible diastereomeric products. And often there's a strong preference for the formation of one diastereomer over the other. Early attempts to predict this outcome were based on empirical observations and led to what's known as Cram's rule. This rule proposed a conformational model where, in the most reactive conformation, the largest group attached to the adjacent stereocenter was positioned anti-opposite to the incoming nucleophile, or eclipsed with the carbonyl oxygen, depending on the specific version of the model. Attack then occurred from the less hindered face of this preferred conformation.
But I feel like I've heard there are more sophisticated and perhaps more generally accurate models used today. Cram's rule was maybe a starting point?
Yes, exactly. While Cram's rule was groundbreaking, the Falcon model, sometimes just called the Falcon model, refined by Ningwe and Trongon, is now more widely accepted and generally provides better predictions. This model suggests the favored conformation for nucleophilic attack has the largest, or most electronegative, depending on the variant, substituent on the adjacent alpha carbon-oriented, perpendicular to the plane of the carbonyl group, not anti. This orientation is thought to minimize unfavorable steric interactions between that large group and the incoming nucleophile as it approaches the carbonyl carbon along its preferred trajectory, the Brigidunitz angle. The nucleophile then attacks from the less hindered face of this conformation. Then there's also the C-plaque model, which offers an alternative electronic explanation based on hyperconjugative stabilization. It suggests the nucleophile prefers to attack from the face that allows for the best stabilizing interaction between the filled sigma bonding orbital of the antiparaplanar bond on the alpha carbon and the developing antibonding sigma orbital of the forming nucleophile carbon bond in the transition state. Usually this means attack is favored opposite the best sigma donor bond.
Wow, so it's not just about physical size, sterics, but also potentially about these subtle electronic effects, like stabilizing electron donations through sigma bonds.
Precisely. Both steric effects, as emphasized by Falcon, and electronic conjugate effects, as emphasized by C-plaque, can be at play, and their relative importance can depend on the specific nature of the substituents, the nucleophile, and the reaction conditions. It's a complex interplay. And critically, we mustn't forget the role of metal counterions often associated with nucleophiles, like Lig+ with LiAlH4 or Mg2+ with Grignard reagents. These metals can chelate, or coordinate, to both the carbonyl oxygen and another nearby Lewis basic group like an oxygen or nitrogen on the substrate. This chelation can lock the molecule into a specific rigid conformation, overriding the preferences predicted by the simpler models. Nucleophilic attack then occurs on the less hindered face of this specific chelated structure, often leading to very high diastereoselectivity. This is known as chelation control.
Okay, let's move back to stereospecific reactions. These are the ones where the stereochemistry of the starting material dictates the stereochemistry of the product through a specific mechanism, right? An unshakable relationship.
That's the idea. For a truly stereospecific reaction, the structural information encoded in the reactant's configuration, like RVSS or EVSZ, is perfectly transferred to the product's configuration following the geometric rules of the reaction mechanism. And a key consequence is that if something causes the reaction mechanism to change, say changing solvents or catalysts, you might lose that stereospecificity entirely. This means knowing the mechanism allows you to predict the stereochemical outcome with certainty. And conversely, observing the stereochemical outcome can give you crucial insights into the underlying mechanism. If an E-alkene consistently gives one specific diastereomer, and the Z-alkene consistently gives a different, distinct diastereomer under the same conditions, that's strong evidence for a stereospecific process.
The bromination of alkenes, adding Br2 across a double bond, is often used as a classic example of stereospecificity, right? I seem to recall something about it always being anti-addition.
It is a classic example, yes. For most simple, unconjugated alkenes, the addition of bromine, Br2, is usually stereospecifically anti. This means the two bromine atoms add to opposite faces of the original double bond plane.
And because it's stereospecific anti-addition, that means starting with E versus Z isomers gives different products, right?
Exactly. The stereochemistry of the alkene directly dictates the stereochemistry of the resulting dibromide product. For example, if you take cis-2-butene, a Z-alkene, and add bromine, the anti-addition results in the formation of a racemic mixture of 2R3R and 2S3S dibromobutane. But if you start with trans-2-butene, an E-alkene, and add bromine, the same anti-addition mechanism leads exclusively to the formation of the acrylmeso 2R3S2-2-3 dibromobutane. This preference for anti-addition also holds for cyclic alkanes. Bromination of cyclohexane, for instance, gives exclusively trans-1,2-dibromocyclohexane via anti-addition.
So this clean anti-addition usually proceeds via a cyclic bromonium ion intermediate, right? A sort of three-membered ring involving one bromine atom and the two carbons of the original double bond.
Yes, the formation of that bridged cyclic bromonium ion intermediate is the key to explaining the anti-stereospecificity. The initial electrophilic attack by Br2 forms this intermediate. The second bromide ion, Br then acts as a nucleophile and attacks one of the carbons from the backside directly opposite to the bridging bromine atom in an SN2-like fashion. This backside attack forces the ring to open and results in the two bromine atoms ending up on opposite faces, hence anti-addition. Now, exceptions can occur, especially if the intermediate bromonium ion is unstable and opens up to form a more stable planar carbocation, perhaps if the alkene has substituents that can stabilize a positive charge. If a carbocation forms, the bromide ion can attack from either face, leading to a loss of stereospecificity and a mixture of syn and anti-addition products.
Okay, how about adding two hydroxyl groups across an alkene to make a diol? We know that can be done, but can we control the stereochemistry? Can we choose whether the two OH groups add syn, same side, or anti-opposite sides?
Yes, we have excellent methods for achieving both syn and anti-dihydroxylation, and they are often stereospecific. One very important method for syn dihydroxylation uses osmium tetroxide, OSO4, often catalytically with a co-oxidant. The mechanism involves a concerted 3+2 cycloaddition reaction between the alkene and OSO4 to form a cyclic osmate ester intermediate. This process inherently adds both oxygen atoms to the same face of the double bond. Subsequent hydrolysis of the osmate ester then yields the syndiol. Because the initial cycloaddition is concerted and stereospecific, a Z-alkene will give a syndiol, while an E-alkene will give an antidiol, which might be meso or racemic depending on symmetry.
Okay, so OSO4 gives syn addition. What about mating the epoxide first? That involves adding an oxygen across the double bond, too.
Right. Epoxidation itself, typically using a peroxy acid like MCPBA, is also a stereospecific syn addition. The oxygen atom is delivered to the alkene face in a single concerted step, forming the three-membered epoxide ring while preserving the original stereochemistry of the alkene, E or Z.
And then if you open that epoxide ring using water, maybe under acidic or basic conditions, what happens to the stereochemistry during the ring opening?
Hydrolytic ring opening of epoxides, particularly under neutral or basic conditions, SN2 mechanism, is typically an anti-addition. The nucleophile, water or hydroxide, attacks one of the epoxide carbons from the backside, causing inversion of configuration at that carbon, while the other carbon retains its configuration as the CO bond breaks. So if you combine a syn epoxidation step with a subsequent anti-hydrolysis step, the net result is an overall anti-dihydroxylation of the original alkene.
Wow. So depending on the reagents and mechanism, we have stereospecific routes to both syn and antidiols. That offers incredible control.
Precisely. To summarize, 1. OSO4 dihydroxylation gives syn addition, xerokine syndiol, E-alkene syndiol. 2. Epoxidation, followed by SN2 hydrolysis, antidiol, gives overall anti-addition, Z-alkene antidiol, E-alkene syndiol. However, a word of caution. If the epoxide hydrolysis is done under strongly acidic conditions, it might proceed via an SN1-like mechanism involving a carbocation intermediate, which could lead to stereorandomization and loss of specificity. So knowing the conditions and mechanism is absolutely crucial for predicting and controlling the stereochemical outcome.
Okay, one more key reaction, hydroboration oxidation. This also adds water effectively across a double bond to give an alcohol. But it has a specific stereochemistry and regiochemistry, doesn't it?
Yep. Yes. It's another cornerstone reaction in organic synthesis with very well-defined stereochemical and regiochemical outcomes. The first step, hydroboration, involves the addition of borane, BH3, often used as a complex like BH3THF, or an alkylborane, like 9-BBN, to the double bond. This addition is a concerted process and occurs with stereospecific syn addition. The boron atom and the hydrogen atom add to the same face of the alkene simultaneously.
Regiochemically, the boron typically adds to the less substituted carbon atom of the double bond due to both steric and electronic factors. This is referred to as anti-Markovnikov regioselectivity.
Okay, so hydroboration is syn addition and anti-Markovnikov. What happens in the second step, the oxidation, usually with hydrogen peroxide and base, does that affect the stereochemistry?
That's the crucial part for the overall stereochemistry. The subsequent oxidation step, which replaces the boron atom with the hydroxyl group, occurs with perfect retention of configuration at the carbon atom where the boron was attached. The OH group effectively takes the exact same spot in orientation as the boron atom it replaces. So the overall sequence provides a stereospecific syn, anti-Markovnikov hydration of alkanes. You add H and OH across the double bond to the same face, syn, and the OH group ends up on the less substituted carbon, anti-Markovnikov.
So if you want to make a specific alcohol product with a specific 3D orientation of the OH group and controlling way it adds, you need to choose carefully between reactions like acid-catalyzed hydration, oxymercuration demercuration, or hydroboration oxidation that give different outcomes.
Exactly. This knowledge of stereospecificity and regioselectivity is fundamental for planning and executing targeted organic syntheses. It allows chemists to precisely control the three-dimensional structure of the molecules they build, which is absolutely vital for creating complex natural products or designing effective pharmaceuticals.
Enantioselective reactions building pure-handedness.
Okay, this feels like the culmination. We take everything we've learned about chirality, configuration, conformation, and reaction mechanisms, and we apply it to the challenge of creating molecules with a specific handedness. Why is this goal so important in the real world?
It's incredibly important because, as we discussed with examples like carvone and pharmaceuticals, often only one enantiomer, one specific hand of a chiral molecule, has the desired biological activity, whether that's a therapeutic effect, a specific flavor, or a fragrance. Synthesizing only that specific active enantiomer, rather than a 50.50 racemic mixture, is often considered a holy grail in modern organic chemistry and drug development. It prevents potential side effects from the unwanted enantiomer, ensures maximum efficacy per dose, simplifies regulatory approval, and represents more efficient synthesis. This is where the field of enantioselective catalysis comes into its own. Using a tiny amount of a chiral catalyst to generate large amounts of a single enantiomer.
We talked earlier about hydrogenation being stereoselective, preferring syn addition from the less injured face. Can it also be made enantioselective? Meaning, can we use hydrogenation to create predominantly one specific enantiomer, R or S, from a procarol starting material?
Yes, absolutely. And this has been a major area of research with tremendous success. The key is to create a chiral environment right at the metal catalyst center where the reaction happens. Most successful approaches use soluble transition metal complexes, often rhodium, ruthenium, or iridium, that incorporate chiral phosphine ligands. These ligands are organic molecules containing phosphorus, and they are specifically designed and synthesized to have a particular stable handedness, chirality. They coordinate to the metal, creating a chiral pocket.
Like those BINAP ligands we mentioned earlier, the ones that are chiral because of their restricted rotation, their atropisomerism.
Precisely. Ligands like BINAP are classic examples. They are chiral due to the restricted rotation around the bond connecting their two naphthol ring systems, giving them a defined helical twist and thus a specific handedness. BNAP, along with many other cleverly designed chiral biphosphine ligands like DIOP derived from tartaric acid, Truffose, BPE, and Dufose, examples shown in scheme 2.1m of the source, coordinate strongly to the metal center. They essentially create a chiral glove or pocket around the active metal site. When the prochiral substrate, like an alkene with appropriate substituents, binds to this chiral catalyst, it can often only do so effectively in one specific orientation due to interactions with the chiral ligand. This preferred binding orientation then dictates that hydrogen addition occurs preferentially from one face of the double bond, leading to the formation of one enantiomer of the product in excess.
How does that work on a detailed molecular level? What determines which face is preferred? Is it just sterics again?
It's often a combination of steric and electronic factors dictated by the precise geometry of the catalyst-substrate complex. For example, in the highly successful enantioselective hydrogenation of certain alpha-beta unsaturated acids using ruthenium BINAP catalysts, the coordination of the substrate's carboxyl group to the ruthenium metal helps to establish a very specific geometry for the bound substrate within the chiral pocket created by BINAP. The subsequent transfer of hydride, hydrogen, from the metal to the alkene's alpha carbon then occurs preferentially via a transition state that minimizes unfavorable interactions with the chiral ligand, dictating the absolute configuration, R or S, of the product formed.
I remember reading about a really detailed mechanistic study involving the hydrogenation of alpha-amidoacrylic acids. It sounded like a surprisingly complex dance between the catalyst, the substrate, and the hydrogen.
Yes, that was a seminal study, particularly on the hydrogenation of methyl Z alpha acetamidocinnamate, using a rhodium catalyst equipped with the chiral dipant P ligand. It provided profound insights into how these catalysts achieve such high selectivity. What's truly fascinating, and perhaps counterintuitive, is that the reactant substrate can actually bind to the chiral catalyst in two different diastereomeric forms. One major complex, more stable, present in higher concentration, and one minor complex, less stable, present in lower concentration. The surprise was that the hydrogenation reaction actually occurs much faster through the minor isomeric complex. This kinetic preference, the minor complex reacting faster than the major one, is what leads to the very high enantioselectivity observed for the product. The major, more stable bound isomer is essentially less reactive, perhaps due to greater steric repulsions in its transition state for hydrogen addition.
So it's not always about which intermediate complex is the most stable, but sometimes about which one reacts the fastest. The kinetically favored pathway wins out. That's a really critical insight.
That's a critical insight indeed, and it came directly from these detailed mechanistic studies. It highlights the absolute importance of understanding the energetics and structures of the transition states, not just the stability of ground states or intermediates, to accurately predict and control stereoselectivity, especially in complex catalytic cycles. It's the height of the energy barrier for the reaction step, not just the depth of the energy well for the intermediate, that dictates the stereochemical outcome when kinetics are involved.
Okay, let's switch back to reducing ketones. We know unhindered ketones usually give racemic alcohols with simple reagents like NaBH4. How do chemists get a specific enantiomer, single-handedness of the alcohol product, from reducing a prochiral ketone?
Again, you need to introduce chirality into the reaction system. This can be done in two main ways, either by using chiral reducing agents or by using achiral reducing agents in the presence of chiral catalysts. Chiral reducing agents have been developed, often derived from naturally occurring chiral molecules like terpenes, from pine trees, for example. Examples include reagents like alpine hydride, derived from alpha pine, and NB-enantride. These reagents have a built-in handedness that influences the direction from which the hydride is delivered to the ketone face, leading to an excess of one alcohol enantiomer. However, their selectivity can sometimes be substrate-dependent.
And what about using catalysts? Are there highly efficient catalytic methods for enantioselective ketone reduction? That usually seems more efficient overall.
Yes, using a small amount of a chiral catalyst to turn over many molecules of substrate is generally preferred. One of the most efficient and widely used approaches involves chiral oxazoborolidine catalysts, like those famously developed by Nobel laureate E.J. Carey and his collaborators, often called Corey-Bakshi-Shibata or CBS catalysts. These catalysts are used in conjunction with an acyryl boron hydride source like borane, BH3, or catechylborane. The CBS catalyst coordinates to both the borane and the ketone, organizing them within a chiral environment. This setup facilitates highly enantioselective hydride transfer to the ketone, consistently achieving very high enantiomeric excesses, often over 95% E, for the reduction of a wide variety of ketones to chiral alcohols.
How do these CBS catalysts manage to achieve such remarkable selectivity? What's their secret mechanism?
Detailed computational studies, combined with experimental evidence, suggest the enantioselectivity arises from a strong preference for the ketone to coordinate to the boron atom of the catalyst in a specific orientation. The bulky groups on the catalyst effectively dictate whether the larger or smaller substituent on the ketone points away from the catalyst core. Hydride transfer from the coordinated BH3 then occurs preferentially to one face of the ketone carbonyl within this organized transition state assembly, specifically the face that minimizes steric interactions with the catalyst's chiral framework. It's a beautiful example of rational catalyst design leading to precise stereo control.
Okay, this next one sounds very familiar from organic chemistry classes. The Sharpless epoxidation, right? Another Nobel-winning breakthrough reaction, I believe.
Yes, absolutely. A truly groundbreaking reaction developed by K. Barry Sharpless, who was indeed awarded the Nobel Prize in Chemistry in 2001, partly for this work on asymmetric oxidation reactions. The Sharpless asymmetric epoxidation uses a combination of titanium tetrasuperpoxide, TiOAPR4, a chiral dialkyl tartrate ester, usually diethyl tartrate DET or disopropyl tartrate DIPT, and tert-butyl hydroperoxide, TBHP, as the oxidant. This system catalyzes the epoxidation of oleitic alcohols, alcohols adjacent to a double bond, to chiral epoxy alcohols with incredibly high and predictable enantioselectivity.
So the chiral tartrate ester is the key. That's the source of the chirality that dictates the handedness of the epoxide product.
Exactly. The chiral tartrate ligands coordinate to the titanium center, forming a chiral catalyst assembly in situ. This chiral titanium complex then orchestrates the reaction by binding both the allylic alcohol substrate and the hydroperoxide oxidant. The specific chirality of the tartrate ligand used, plus dicyclosdiol or dicystetyl, dictates the facial selectivity. The orientation of the reactants within the catalyst's active site is precisely controlled by the tartrate's handedness, leading to a highly favored transition state for oxygen transfer to one specific face of the double bond, resulting in one major epoxide enantiomer. The titanium also acts as a Lewis acid to activate the peroxide, making the oxygen transfer both efficient and highly enantioselective. The predictability is remarkable. Plus, tartrate generally delivers oxygen from one face, and tartrate delivers it from the opposite face.
That's just amazing control over the 3D outcome. It feels like molecular engineering at its finest.
It really is. It's a prime example of how carefully designed chiral catalysts can translate the subtle principles of molecular geometry and interaction into highly specific and predictable chemical outcomes. It allows chemists to synthesize valuable enantiopure building blocks, epoxy alcohols, from readily available starting materials, revolutionizing synthetic strategy.
And Sharpless didn't stop there. He also developed a related method to make chiral diols enantioselectively from alkenes, which is equally impressive.
Yes, the Sharpless asymmetric dihydroxylation, often abbreviated as the AD reaction, is another masterpiece from his group, building on the chemistry of osmium tetroxide. This reaction uses a catalytic amount of OSO4 along with specific chiraligens derived from cinchona alkaloids, natural products related to quinine. The most common ligands are based on dihydroquinone DHQ and dihydroquinidine DHQD, often linked together via a phthalazine, PHU, or other spacer unit like DHQ2-phenyl and DHQD2-phenyl. These ligand-OSO4 combinations catalyze the syn-dihydroxylation of a wide range of alkenes, not just allylic alcohols, to produce chiral diols, again with consistently high enantiomeric excess. Pre-mixed formulations like 80-mixo and 80-mixa make the reaction very user-friendly.
So similar to the epoxidation, the specific chiral alkaloid ligand you choose, DHQ versus DHQD, determines the handedness of the diol product.
Absolutely. DHQ and DHQD are pseudoenantiomers, and they induce opposite facial selectivity in the dihydroxylation reaction. So you simply choose AD-mixa, containing the DHQ-based ligand, or AD-mixo, containing the DHQD-based ligand, depending on which enantiomer of the diol you want to synthesize. The mechanism is complex, but involves the chiral amine ligands accelerating the catalytic cycle and creating a chiral binding pocket for the alkene substrate as it approaches the osmium center for the initial 3+2 cycloaddition. Empirical mnemonic devices, beautifully supported by computational modeling, help predict which face of a given alkene will react preferentially based on attractive non-bonded interactions, such as pi-p stacking between the alkene and the aromatic quinoline rings of the ligand within the catalyst binding site.
Are there significant practical applications for this AD reaction beyond just being elegant chemistry?
Oh, many. It's become a workhorse reaction in organic synthesis for installing stereogenic centers. It's been applied in countless synthetic sequences towards complex natural products and pharmaceuticals. A notable and highly impactful example mentioned in the source is its use as a key starting point for developing efficient enantioselective syntheses of important non-steroidal anti-inflammatory drugs, NSAIDs, like S-ibuprofen and S-naproxen. As we know, often only the S-enantiomer of these drugs is pharmacologically active, so being able to synthesize it directly using the AAD reaction provides a significant advantage over producing and separating racemic mixtures.
Okay, this leads to an interesting scenario. What happens when you have multiple stereochemical factors potentially influencing a reaction? For instance, maybe your starting molecule already has a chiral center, and you're using a chiral reagent or catalyst. How do you know which factor wins out? Which one dictates the stereochemical outcome?
That's a great question, and it's crucial in practical synthesis. It's often very useful to classify the observed stereoselectivity in such cases as being either primarily substrate-controlled or primarily reagent-controlled. This classification helps chemists understand the dominant factors at play and rationally design their synthetic strategies.
Can you explain the difference between substrate control and reagent control?
Sure. In substrate control, the existing stereocenters or specific structural features within the reactant molecule itself are the primary factors dictating the stereochemical outcome of the reaction. The inherent shape and chirality of the substrate guide the reaction preferentially towards one diastereomeric product. Think back to Cram's rule or the Felkinon model for additions to chiral ketones that's largely substrate control. In reagent control, on the other hand, the chirality of the external reagent or catalyst being used is the dominant factor influencing the stereochemical outcome. A powerful chiral reagent or catalyst can often override any inherent stereochemical bias present in the substrate. For example, in the sharpless asymmetric dihydroxylation AD reaction of an alkene that already possesses a stereocenter, the choice of the AD catalyst, AD mixes versus AD mixes, can usually strongly determine which diastereomer of the product diol is formed, regardless of the substrate's own preference. This makes the AD reaction predominantly reagent-controlled.
And what if the substrate itself doesn't have a built-in stereocenter to begin with, but you still need to create a new chiral center with a specific handedness using an acyl reagent?
This leads to the very clever and widely used strategy of employing chiral auxiliaries. These are chiral molecules that are temporarily attached covalently to the acyl reactant molecule. This auxiliary then acts as a chiral handle, directing subsequent reactions like analyte alkylation, Diels-Alder reactions, or aldol additions to occur preferentially on one face of the molecule, thereby inducing chirality. Once the desired new stereocenter has been formed with the correct handedness under the influence of the auxiliary can then be easily cleaved off, leaving behind the desired enantiopure or enantiomerically enriched product. Popular examples include chiral oxazolidinones, like Evans auxiliaries, and sultams, like a pulsar sultam. They work by creating a specific rigid conformation, often involving chelation, that sterically blocks one face of the reacting center, forcing the acyl reagent to attack from the other, unhindered face. It's like temporarily putting a special-shaped glove on your molecule to guide its reaction, then taking the glove off afterwards.
Special topics and advanced concepts.
We touched briefly on how important it is to know the enantiomeric purity, the EE, of a sample, especially for things like drug development. What are the specific practical tools chemists use routinely to measure this purity, going beyond just the classic polarimeter?
Right, polarimetry gives you the net rotation, but determining the actual EE requires knowing the rotation of the pure enantiomer, which isn't always available or easy to measure accurately. Plus, polarimetry isn't always sensitive enough for small amounts or weakly rotating compounds. So NMR spectroscopy has become an invaluable tool, particularly with the clever use of chiral shift reagents, CSRs, and chiral solvating agents, CSAs.
How do those actually work with NMR? NMR is normally so sensitive to the local electronic environment around a nucleus. How does adding something chiral help?
It works by creating diastereomeric environments for the two enantiomers in the NMR tube. Chiral shift reagents are typically paramagnetic lanthanide metal complexes, often europium or praseodymium, coordinated to chiral ligands. These CSRs can reversibly bind to Lewis basic functional groups, like alcohols, amines, ketones, esters, in the analyte molecule. Because the CSR itself is chiral, it forms two different diastereomeric complexes with the R and S enantiomers of the analyte. Since diastereomers have slightly different physical properties and shapes, the lanthanide metal induces slightly different shifts in the NMR signals of the protons, or other nuclei, in the two enantiomers. This causes signals that were identical for the R and S enantiomers in the absence of the CSR to split into two distinct signals. The ratio of the areas of these split signals directly corresponds to the enantiomeric ratio and thus the E. Common CSRs mentioned are UTFC3 and UHSC3. The source shows a dramatic spectrum where the signals for D and L asparagine are clearly separated by a CSR.
Okay, that's clever, creating temporary diastereomers. What about chiral solvating agents? Are they similar, but maybe without the metal complex involved?
Yes, that's the basic idea. Chiral solvating agents are chiral molecules that don't form coordinate bonds with the analyte, but interact through weaker, non-covalent forces, like hydrogen bonding, dipole interactions, or pi p stacking. If the interaction solvation between the chiral solvating agent and the two enantiomers of the analyte is strong enough and geometrically specific enough, it creates slightly different average magnetic environments for the nuclei in the R and S enantiomers. This again can lead to separation or splitting of their NMR signals, allowing for EE determination. The famous Perkel alcohol, 1-9-anthral 2-2-2-trifluoroethanol, is a well-known CSA. It has a trifluoroethanol group designed for hydrogen bonding and a large anthracene ring system that can induce different shielding effects, anisotropy, and engage in pi-pi stacking interactions differentially with the two enantiomers of the analyte. Various chiral amines and amidides can also serve as effective CSAs.
So really, all these NMR methods and chromatographic methods too rely fundamentally on exploiting the subtle differences in how the two enantiomers interact physically or chemically with a chiral environment, whether it's a shift reagent, a solvent, or a stationary phase.
Exactly. It all boils down to chiral recognition, the ability of one chiral entity to interact differently with the two enantiomers of another chiral entity. These differential interactions, however slight, are the basis for virtually all methods of enantiomeric analysis and separation.
Okay, so we can measure the purity using these sophisticated tools, but how do you actually separate the two enantiomers on a larger preparative scale? Say you've made a kilogram of a racemic drug mixture, but you only need the R enantiomer. How do you get it pure?
The classical tried-and-true method is resolution via diastereomer formation. The strategy is to react your racemic mixture, R plus S, with a readily available enantiopure substance called a resolving agent, say pure R. This reaction forms a mixture of two diastereomers, RR and SR. Now, crucially, unlike enantiomers, diastereomers have different physical properties, different solubilities, different melting points, different boiling points, different chromatographic behavior. This difference allows you to separate the two diastereomers using standard laboratory techniques like fractional crystallization or chromatography. Once you have separated the diastereomers, say you isolate pure R, you then perform a second chemical reaction to cleave off the resolving agent, regenerating your desired enantiomer in pure form. It's often laborious but effective.
That's a very clever multi-step approach. But what about direct physical separation methods? Can you separate enantiomers directly without having to form diastereomers first?
Yes, and this is where preparative chromatography using chiral stationary phases, CSPs, truly shines, especially in the pharmaceutical industry. Just like the analytical HPLC methods we discussed, the column packing material, the stationary phase, is itself chiral. As the racemic mixture flows through the column with the mobile phase, the two enantiomers interact differently with the chiral stationary phase. One enantiomer might bind slightly more strongly or reside longer in the chiral pockets of the CSP than the other. This difference in interaction strength causes the two enantiomers to travel through the column at different rates, allowing them to be separated and collected as distinct fractions. Hydrogen bonding, pipey stacking, dipole interactions, and steric fit are often the key intermolecular forces responsible for this chiral recognition on the CSP.
Like those commercially available chiral cell and chiral pack columns? I've seen those names.
Yes, exactly. Those are very popular and effective CSPs based on derivatized polysaccharides, like cellulose or amylose coated on a silica gel, that form a complex chiral superstructure, almost like a chiral lattice. There are also many synthetic brush-type CSPs, where chiral molecules, often based on amino acids or other chiral building blocks, sometimes mimicking the Perkel alcohol concept, are covalently bonded to the surface of silica particles. These are often designed to maximize specific interactions like pi-pi interactions and hydrogen bonding with particular classes of analytes, such as NSAIDs like naproxen and ibuprofen, whose chiral separation is very important.
And you mentioned capillary electrophoresis for analysis. Can that be used for preparative separation too? It sounds like a high-resolution technique.
CE has indeed been adapted very successfully for chiral separations, offering extremely high resolution, separation efficiency. It relies on the differential migration of charged molecules, or neutral molecules complex with charge selectors, through a narrow capillary filled with an electrolyte buffer and often a polymer matrix, under the influence of a high electric field. To achieve chiral separation, a chiral selector is added to the buffer electrolyte. Common selectors include cyclodextrins, toroidal molecules made of glucose units with a chiral cavity, chiral crown ethers, or even macrocyclic antibiotics like vancomycin. The two enantiomers of the analyte interact or bind differentially with this chiral selector in the buffer. This difference in binding affinity affects their overall charge-to-size ratio or their interaction with the capillary wall matrix, causing them to migrate at different rates towards the detector. CE offers advantages like very high enantioselectivity, speed, and low sample solvent consumption, making it excellent for analysis. Scaling it up for large-scale preparative separation is generally more challenging than with chromatography, but it is possible for smaller quantities.
You mentioned enzymes earlier as highly selective catalysts. Can they also be used specifically to distinguish between enantiomers or even to help create chiral molecules from non-chiral starting materials in a controlled way, using nature's catalysts?
Oh, absolutely. Enzymes are nature's masters of chiral recognition. They are inherently chiral molecules, proteins, with exquisitely defined three-dimensional active sites. This allows them to be incredibly selective, often binding or reacting with only one enantiomer of a chiral substrate, sometimes with near-perfect discrimination. They can be used for kinetic resolution, where the enzyme selectively reacts with one enantiomer in a racemic mixture, leaving the other enantiomer unreacted and allowing for their separation. Or perhaps even more powerfully, they can perform desymmetrization, also called asymmetrization, of prochiral or meso compounds. Here, the enzyme selectively modifies one of two identical enantiotopic groups within a symmetrical molecule, directly converting it into a single enantiomer of a chiral product.
So desymmetrization means they can essentially take a non-chiral molecule that has the potential to become chiral and convert it directly into a single specific enantiomer. That sounds far more efficient than making a racemic mixture and then having to resolve it, where you lose at least half your material.
Yes, exactly. If the enzyme's selectivity is high enough, desymmetrization can provide direct access to enantiomerically pure compounds from acryl precursors, potentially achieving up to 100% theoretical yield of the desired enantiomer. This is often much more atom economical and efficient than classical resolution or kinetic resolution, which has a maximum theoretical yield of 50% for the desired enantiomer from a racemate, unless coupled with racemization. Sometimes chemists cleverly combine enzymatic kinetic resolution with an in situ chemical or enzymatic racemization step for the unreacted starting material. This is called dynamic kinetic resolution, DKR, and it allows, in principle, for the conversion of an entire racemic mixture into a single desired enantiomer, overcoming the 50% yield limit of standard kinetic resolution.
What are some of the most versatile or commonly used enzymes for these kinds of stereoselective transformations in the lab or industry?
Lipases and esterases are perhaps the most widely applied class. They catalyze the hydrolysis of esters, or in reverse, the formation of esters, transesterification. They are attractive because many are commercially available at low cost, are relatively stable, often function well even in organic solvents, which can be advantageous for substrate solubility, and frequently exhibit broad substrate specificity coupled with high enantioselectivity. They employ a well-understood catalytic triad mechanism involving specific histidine, serine, and aspartic acid residues in the active site to efficiently transfer acyl groups.
Like the famous pig liver esterase, PLE, I think I've heard of that one being used a lot.
PLE is a classic and very common example, yes. It has been extensively used for the kinetic resolution of chiral alcohols and esters, and particularly for the enantioselective desymmetrization of mesodiesters, such as derivatives of glutaric acid or cyclic mesodiols. There are even predictive active site models for PLE, developed by Jones and others, that help rationalize and predict its stereoselectivity based on visualizing hydrophobic and polar pockets within the enzyme's binding site. Porcine pancreatic lipase, PPL, represents another important group of lipases frequently used in organic synthesis. Lipases are often activated by conformational changes that occur at hydrophobic interfaces, like oil water, which can influence their activity and selectivity depending on the reaction conditions.
And what about other types of enzymes beyond lipases and esterases? What about ones that work on amides or other functional groups?
Certainly. Proteases, which naturally hydrolyze peptide bonds, and acetylases, which hydrolyze N-acyl amino acids, are important for transformations involving amino bonds. While proteases can be very specific for certain amino acid sequences, acylases, particularly aminoacylases, are widely used for the large-scale industrial preparation of enantiopure alpha amino acids, like L-methionine or L-valine, via the resolution of racemic N-acetylated amino acids. Acylases are also employed in the synthesis of semisynthetic antibiotics, like penicillins and cephalosporins. For example, E. coli penicillin acylase is used industrially to hydrolyze the naturally occurring phenylacetyl side chain from penicillin G, providing the crucial 6-aminopenicillinic acid, 6-APA core, which can then be reacylated with modified side chains to create important drugs like amoxicillin or ampicillin.
What about epoxides? Can enzymes help with the selective synthesis or opening of those important chiral building blocks too?
Yes, epoxide hydrolases, EH, are enzymes that catalyze the hydrolytic ring opening of epoxides to form vicinal diols, 132 diols. Their natural function is often detoxification, breaking down potentially harmful epoxides formed metabolically. They also typically use a catalytic triad mechanism, but distinct from serine hydrolases like lipases. EH enzymes usually employ an aspartate carboxylate group as the initial nucleophile to attack the epoxide. Different epoxide hydrolases, sourced from various organisms like rodent livers, bacteria, or fungi, exhibit varying substrate specificities and antioselectivities, often depending on factors like the substrate chain length or substitution pattern. They are frequently used in kinetic resolutions of racemic epoxides, selectively opening one enantiomer to a diol while leaving the other epoxide enantiomer untouched. They can even be used in clever sequential reaction schemes, as shown for a precursor to the drug eleprodil, to achieve near-complete conversion of a racemate into a single enantiomerically enriched product. They offer a green and often highly selective route to chiral epoxides and diols.
Okay, let's shift to a slightly different, more subtle topic. The book talks about the anomeric effect. This sounds like one of those more advanced, perhaps counterintuitive stereoelectronic effects. What exactly is it?
It is indeed a fascinating and important stereoelectronic effect, particularly prominent in cyclic compounds containing heteroatoms adjacent to an electronegative substituent, most famously in carbohydrate chemistry, sugars. In essence, the anomeric effect describes the observed thermodynamic preference for certain substituents located at the anomeric position, that's C1 in aldopyranose sugars, the carbon attached to two oxygen atoms, to adopt an axial orientation rather than the sterically expected equatorial orientation. So, it often dictates a conformation that seems counterintuitive based purely on minimizing steric bulk.
So it's basically an exception to the general rule we learned for cyclohexane, where bulky substituents strongly prefer the equatorial position to avoid 1,3 diaxial interactions. The anomeric effect makes axial more stable.
Exactly. It often overrides the simple steric argument. Scheme 2.16 in the source provides striking examples. It shows various two-substituted tetrahydropyrans, rings with one oxygen, halogens, like Cl-Br, or alkoxy groups, like OCH3 at the C2 position, analogous to the anomeric position, show a significant preference for the axial position over the equatorial one. For instance, 2-chlorotetrahydropyran exists predominantly with the chlorine atom axial. The magnitude of this effect depends on the nature of the substituent. More electronegative groups often show a stronger effect, and also notably decreases in more polar solvents, which suggests electrostatic interactions play a role.
What are the telltale structural clues, maybe from experimental data like X-ray crystallography, that indicate the anomeric effect is operating, beyond just observing the preferred axial conformation?
Changes in bond lengths are a key structural signature. Typically, when the anomeric effect is strong and favors the axial conformer, the bond between the anomeric carbon and the axial substituent, the exocyclic CX bond, is often found to be longer and weaker than expected for a typical single bond. Concurrently, the bond between the anomeric carbon and the ring heteroatom, the endocyclic CO bond in a pyranose, is often shorter and stronger than usual. The more electron withdrawing the axial substituent X is, the more pronounced these bond length changes tend to be. This suggests a redistribution of electron density is occurring. Correction. The original outline in my previous thoughts misstated the bond length changes. The prevailing explanation involves donation from the ring oxygen to the CX sigma star orbital, which should lengthen the CX bond and shorten the CO bond. Let me correct that going forward.
Okay, so the axi-CX bond gets longer and the ring CO bond gets shorter. Why does this happen? Is it just about dipoles repelling each other, trying to get further apart?
The classical explanation did involve dipole repulsion. In the equatorial conformer, the dipoles of the ring CO bond and the CX bond might be somewhat aligned, leading to repulsion. In the axial conformer, these dipoles are oriented differently, potentially reducing this repulsion. This explanation helps account for the observed solvent dependence. Polar solvents stabilize dipoles and reduce the effect. However, electrostatic interactions alone aren't considered sufficient to fully explain the magnitude and structural consequences of the anomeric effect. The prevailing, more modern explanation is based on stereoelectronic orbital interactions, specifically N's hyperconjugation.
Okay, let's unpack that orbital interaction. What does N's hyperconjugation mean in this context?
From a molecular orbital perspective, it involves an interaction, a delocalization of electrons between an occupied non-bonding N lone pair orbital on the ring heteroatom, like the oxygen in a sugar, and the adjacent empty antibonding sigma star orbital of the CX bond, where X is the electronegative substituent at the anomeric position. This type of stabilizing interaction is most effective when the lone pair orbital and the S orbital are aligned antiparaplanar, roughly 180 degrees apart. This optimal alignment occurs precisely when the electronegative substituent X is in the axial position. This N electron donation effectively puts electron density into the CX antibonding orbital, which weakens and lengthens the CX bond. Simultaneously, it removes some electron density from the oxygen lone pair, which results in a shortening and strengthening of the ring CO bond. This orbital explanation beautifully rationalizes the observed bond length changes and the preference for the axial conformer. It's analogous to the hyperconjugation we discussed stabilizing staggered ethane.
So it's really a quantum mechanical effect, a subtle electron delocalization that explains the seemingly odd conformational preference. It's not just about atoms bumping or dipoles repelling.
Precisely. It's a beautiful example of how understanding orbital interactions is crucial for explaining molecular structure and stability. Computational studies strongly support this orbital interpretation, confirming the stabilizing energy contribution from this nice delocalization in the axial conformer. While opposing electrostatic and steric effects certainly modulate the overall magnitude of the anomeric effect and can sometimes even reverse the preference for certain substituents, this fundamental electronic stabilization is believed to be the primary driving force. It's also observed involving other heteroatoms like sulfur and nitrogen, occurs in 5-membered rings as well, and is even considered important in dictating the preferred conformations of nucleosides and nucleotides, thus influencing the structure of DNA and RNA.
Okay, one last area from this chapter. We talked about steric and torsional effects influencing how hydrides reduce ketones, especially cyclohexanones. What about the influence of polar substituents elsewhere on the ring? Do they exert effects beyond just simple sterics?
Yes, they certainly can. Polar substituents, even if they are remote from the carbonyl group, can introduce significant electrostatic effects based on the magnitude and orientation of their bond dipoles relative to the reacting carbonyl group. For instance, in substituted cyclohexanones, placing an electronegative substituent like HOCH3-F-DoxyLPr in an equatorial position, particularly at C3 or C4, can shift the reduction ratio towards increased equatorial approach by the hydride nucleophile, leading to more axial alcohol. This is thought to occur because the dipole of the equatorial CX bond has a component that points towards the carbonyl carbon, effectively making the equatorial face slightly more electron-rich, and thus repelling the negatively charged incoming hydride nucleophile. The observed order of this effect often aligns with the component of the bond dipole opposing the nucleophile's approach.
And what if that polar substituent is in an axial position instead? Does it have the opposite effect?
Generally, yes, although it's a bit more complex. Axial electronegative substituents, with the interesting exception of fluorine, which often behaves unusually, tend to favor increased axial attack by the hydride, leading to more equatorial alcohol. This might be explained by the axial CX bond dipole having a larger component perpendicular to the carbonyl group, potentially polarizing the carbonyl or stabilizing the transition state for axial attack differently than an equatorial substituent does.
So are these effects purely electrostatic field effects operating through space, or are orbital interactions involved here too?
That's a subject of ongoing discussion and research. It's likely a combination. While through space, electrostatic interactions undoubtedly play a role, orbital interactions, like hyperconjugation involving the polar substituents bond orbitals and the carbonyl pi system or the transition state orbitals, are also likely involved. There's debate about whether these are primarily ground state effects. For example, the polar substituent slightly distorting the shape or pyramidalization of the carbonyl carbon before reaction, or transition state effects. Example, stabilizing or destabilizing the developing charge in the transition state. For example, studies on the reduction of substituted atom antagonies, rigid cage systems where conformations aren't an issue, show that electron-attracting groups promote addition from the syn phase, while electron-donating groups promote addition from the antiphase, even when the substituent is quite remote from the reaction center. This strongly suggests that polar electronic effects, transmitted perhaps through the sigma bond framework or through space, are definitely at play.
This really underscores that predicting or understanding reactivity requires a truly nuanced look at all these interacting forces, sterics, torsional strain, electrostatic fields, orbital interactions. It's a complex molecular dance.
It truly is. The final stereochemical outcome of many reactions, especially additions to carbonyls or alkenes in cyclic systems, is determined by the subtle interplay of all these factors. For cyclohexanones, we've seen axial attack is often preferred by small hydrides due to minimizing torsional strain, but steric factors, using bulky reagents or having bulky ring substituents, can force equatorial approach. And now we see that polar substituents can further modulate this balance through electronic effects. Similarly, in bicyclic ketones, electronic effects often play a dominant role. It's this complex but fascinating interplay that chemists constantly strive to understand, predict, and ultimately harness for synthetic control.
Wow, what an absolutely incredible journey deep into the heart of molecular structure and reactivity. We've gone from understanding the fixed-handedness of molecules, their configuration, to seeing how they twist and turn in these dynamic conformational dances, and ultimately how chemists can actually control these behaviors to build very specific molecules with desired shapes and properties.
It really is a field where geometry truly meets function, isn't it? We've seen time and again how tiny details, just the arrangement of atoms in 3D space, can have absolutely profound implications for a molecule's properties.
Yeah.
Everything from its smell,
like carvone, to its crucial medicinal effects in pharmaceuticals.
And the tools chemists now have to understand and predict this, from sophisticated NMR techniques that can almost freeze molecular motion to incredibly powerful computational methods like molecular mechanics and QMMM, allow for the design of reactions with truly remarkable precision. Knowing these principles of stereochemistry and conformation is absolutely key to rational drug design, materials science, catalysis, and so much more.
It really makes you wonder, though, what other subtle molecular forces or interactions might still be at play that we haven't even fully uncovered or understood yet? What secrets are still hidden in these molecular dances, just waiting to unlock completely new avenues in chemical synthesis and discovery?
That is definitely food for thought. You've just taken a deep dive into the fascinating world of stereochemistry, conformation, and stereoselectivity, guided by Chapter 2 of Carey and Sundberg. Thank you so much for joining us on this exploration of molecular wonders.
Until next time, keep exploring, keep questioning, and keep learning.
This has been The Deep Dive.